Thanks everyone for joining. My name is Egor. I'm the co-founder and CTO at Bigeye, and today we're going to be talking about how to make the backfill process a little bit less painful. If you're a data engineer or have had to deal with data, I'm sure you are familiar with backfilling data and correcting it historically. So today I'm going to talk a little bit about tips and tricks to make it a little bit easier. I love to keep this as interactive as possible. If you have any questions, feel free to put them into the Q&A section, and I am happy to take them as we go. And if I miss anything, I will make sure I address them at the end, and I'll have another call for questions at the end of the session. So with that, let's get started. As I mentioned, my name is Egor. I am the co-founder and CTO here at Bigeye. Before Bigeye, I was at Uber, where I was one of the first people called a data engineer. I stood up the original data warehouse there, and then from there built a lot of analytics and data-based tooling for the rest of the company embedded in teams and within the data platform itself. At the end of this session, I'm going to actually walk through one of the projects that I did around experimentation analytics and how we scaled our data processing there, especially around backfilling the data and correcting it historically as necessary. So what are we talking about today? We are going to talk about why backfilling sucks and why it doesn't always have to. I personally love this meme. This is Fine Dog is probably one of my favorite depictions of life as a data engineer, where everything around you is on fire all the time and you just kind of put on a happy face and say, yep, this is fine, we'll move on from this as well. And backfilling is definitely one of those concepts, but we can talk a little bit about how you can do work ahead of time in order to make backfills a little bit easier. So we're going to have three sections today. First one, we'll talk about techniques. So this is going to be how to process and store the data in order for you to make it easy to have an easier time backfilling it, in order to not be sort of stuck in a paradigm that makes it very complex to reprocess data historically. We're going to talk about the tools that you're probably already using or may want to use, some existing frameworks that are popular, as well as some scripting that you might want to roll in on your own and extend your current frameworks or any other tooling that you're already using. And finally, we're going to talk through that real world example to bring it all together. As I mentioned, this is based on my time on the experimentation analytics team at Uber, and we'll talk about how we set ourselves up for success early when we were building out the processing pipeline so that backfills became quite a bit easier. So start off with techniques. Let's talk about processing the data itself. So why are we even talking about backfills? Well, let's take a quick step back and talk about the different ways that data is processed. So if your data is very small or if it changes all of the time historically, then full reloads are actually not a problem. Reprocessing all data for all history is a very easy paradigm. There's never a need to actually reprocess history, because every single time your processing runs, it already processes all historical data. So you're always going to have the most up-to-date data with a full reload. However, as you scale and as the volume of data increases, it could become very expensive to do this at scale. However, sometimes it may simply be required, especially for dimension tables. So going back to an example, if you have, let's say, an e-commerce store and you have your users and you have your orders, users are going to scale fairly slowly, and properties about users can change at any point in time for any user in all history. Therefore, full reloads for your user dimension table are usually a good call. However, your orders table may start small and you could reprocess it completely into a fact table and roll it up into an analytics table at any point in time. Maybe you can reprocess all of your history, but at some point you're going to scale to the point where it's prohibitively expensive from a computational perspective to actually scale out the reprocessing your orders table. And that's why there are incremental updates, which is processing only the newest data that is available to you. So this is something that is cheaper computationally and it scales really well, but the logic around it becomes much more difficult because you have to start reasoning about what inputs you need to take in order to correctly process the right amount of new arriving data. So a lot of this is figuring out when the last time the job ran, what new data has arrived since then, what parts of the data may or may not be updated historically. And whenever something changes, let's say your business logic changes or updates, or you're remapping a new column to an enum and you're changing the output values, you might need to reprocess historical data. And this is really what I mean by backfilling, is anytime you have to reprocess historical data. I know the word backfill traditionally means when you miss a certain time window of data and you want to literally fill in that time window that you missed. But when I'm referring to backfilling, I really mean anytime you have to reprocess it, whether it's because you missed it or because you are changing logic and you want the output to look slightly different. So let's move on to from this, and we will mostly be talking about incremental processing today, and talk about how you can optimize your data storage in order to improve your ability to backfill. So let's talk about, in this case, we're talking about partitioning. Partitioning is particularly important for incremental processing because it allows you to separate your data on some predefined field. And so usually this is both logical and physical separation, meaning you have to query specific partitions, but also physically when they're stored on disk, they are usually separate files completely there, or folders. And usually this is a data or a timestamp. So in this screenshot, you can see a table with users by date. And if you partition it, in this case, by the month that the user signed up, you can actually see the 3 different partitions that exist there, each with all of the data for that month. Now, partitioning is particularly important for incremental processing because it allows you to only update the parts of the data that you care about. So if you're processing 1, 2 days at a time, 3 days at a time, you're only touching those 3 physical partitions without changing anything else historically. This allows for much faster reads and writes, especially if you're accessing a limited number of partitions. Typically, you want to limit this to as few as possible, but some systems will allow you to scale that part up. And this is really available in most data warehouses. Snowflake's a little bit special here because they have their own notion of micro partitions and you can't control that. Snowflake sort of decides for you how they want to lay out your data on disk and which partitions will be read and written into. But if you're using something like BigQuery or Databricks or any other S3-based or HDFS-based data warehouse or data lake, then you are probably already partitioning your data because those are fairly native concepts in those systems. And finally, partitioning allows you to backfill one partition at a time, which, as I mentioned, creates faster writes, but it also introduces a unit of parallelism that you can exploit in the future by, by parallelizing how many backfills you're running simultaneously. And if they're all touching partitions that are completely disjoint, which in this case, all partitions have to be completely disjoint, then you can achieve much faster backfills, especially when they're over a longer period of time than you would otherwise. So now that we know about how to store the data more efficiently for incremental processing and backfilling, let's talk about how to optimize our transformations for backfilling and incremental processing. So there's really two parts to this that are important. One is how you're expressing the business logic in your data processing. And the second one is how you're accessing the input data for your transformations in your data processing. So let's start with the business logic. And the one thing that I could come up with when I was putting this together is the most important thing is to use idempotent and pure functions only. So let's break this down. First off, idempotent, what does that mean? It means rerunning the same function, the same logic is going to produce the same result no matter how many times you run it. So a counterexample to this is x equals x plus 1. In SQL, this might be case when column is not 0, then column equals column plus 1. So this is a not idempotent function. If I rerun this 5 times, x will have incremented 5 times and be 5 larger than it was to start with. The reason idempotent functions are problematic is because when you go to backfill, when you reprocess your data, you're going to run into cases where you change data in a way that you do not expect. You want most of your logic to result in the same thing no matter how many times you run it. Because let's say you needed to backfill something and then you updated your logic and reran it again. You don't want the result to be changing every single time you rerun that processing on that partition. Secondly, pure functions mean that the function will have the same output for the same input. And now most transformation that you're doing is probably already pure. We're talking about remapping, for example, country codes to country names, or mapping IP addresses to regions. These are pure functions for the most part. I'm not going to get into the IP range problem, but these are pure functions that will always produce the same output for the same input. But a good counterexample to this is anything that uses current timestamp or current date or some environmental variable that changes. These aren't pure functions because their output will depend on the state of the system at the time. So for example, if you're computing churn using current timestamp and you're saying user, when a user left the system and deleted their account compared to current timestamp and take the time difference of that, if I run that today and if I run that tomorrow, I'm going to get different results. And that's not going to be good because let's say I have a user that churned a month ago and I need to reprocess the partition for that information, then my days since churn is going to be different after I rerun it, because even though I have the same input of the same user, I do not have the same output because I have a variable that is dependent on the environment and that is always changing with every processing. So once you've locked down your business logic into only using pure idempotent functions, then you can you need to make sure that you can parameterize your input data. So the important part of incremental processing, as I mentioned in a couple of slides ago, is the fact that you need to decide which data you read every single time you run that incremental processing. And part of that is parameterizing that usually across time ranges. Going back to that orders example, if I have orders coming in every day, I might want to process the last week of orders because maybe orders can get backfilled and their status can change in the system. Or I might want to reprocess the last 3 days of orders or 1 day of order or 2 hours of orders. But that logic needs to be parameterized because I will want to be able to process some arbitrary time range, especially when I'm backfilling. And when I'm backfilling, I want to not just process the last 7 days. I might want to say, I want to process the 7 days from a month ago. So by parameterizing that the range of data that you're accessing, you're allowing yourself to have an easier wait time backfilling and reprocessing the historical data. And then it's just important to default to something that works for that ongoing process. In my example, the default might be everything from 7 days ago until now. And that now is that default. And then otherwise you can change the end timestamp and parameterize it as you see fit. So we've talked a little bit about storing your data efficiently, building transformations so that you don't shoot yourself in the foot later when you're backfilling. So let's talk a little bit about the sort of tools that you're going to encounter and how you can apply these techniques in those tools. So first off, we'll just talk about frameworks. There's really two things that matter here, and one is the processing frameworks. So how do you express your business logic in your transformations? And the second one is all your orchestration and execution frameworks. So that are going to actually run that transformation and processing both on a day-to-day basis and maybe even for backfilling. So let's start with the processing frameworks. Really, this is where there's going to be two camps. One camp is going to be the code-based processing frameworks. We're talking typically Spark, but also MapReduce, Pig, Pandas, anything that is code-based. I'm going to read a bunch of data and run code-based transformations. Now, this is usually easier to test and control because your transformations and your logic is now expressed as Python or as Java or Scala, and you can create functions around those and just test those functions independently, make sure they're pure, make sure they're idempotent, and know that your transformations are doing the right thing. Now, and parameterization there becomes very easy. Typically, that's a built-in function of all languages. You can pass around parameters into functions, which then generates the right input data sets for you. SQL-based processing frameworks are a little bit tricky because it becomes practically impossible to test individual transformation logic. And at this point, you need to mostly test and validate it, the output of the system. Parameterization also becomes a lot trickier, and you typically need a layer on top of it. So you need a framework that helps you do the parameterization of your SQL queries before they're being executed. So for this, if you haven't heard of it, DBT, it stands for Data Build Tool, is a great framework for helping you build SQL-based transformations and logic around your models. It takes care of the parameterization for you, and it helps you work through a lot of the trickiness around incremental processing that you might encounter otherwise. And also what we've seen a lot is a lot of folks just build their own SQL-based parameterization framework and templating and some sort of Jinja-based SQL generation framework that can help. But the important thing to understand here is you will need to scale this out and it will become extremely complex. But if you are building your own, then at least take into account the fact that you are going to need to parameterize your input data sets, and you have that as a first-class feature in your in-house framework. Finally, once you've actually built out your logic, you know what it looks like, you know what it's written in, it's all there, something needs to go and run it, both on a day-to-day basis and, as well as whenever you want to backfill it. And ideally, your day-to-day processing is the same as your backfilling logic. Those two should be pretty much exactly the same from a logic perspective, just not from an input perspective. So for orchestration, you guys schedule a day-to-day processing, and you need to be able to pass those parameters into your code. As we said, we're parameterizing those input data sets. We need something to pass in what parameters are running or the defaults. And so typically orchestration frameworks have some way to pass parameters into the jobs that they're running. Airflow is the most common example here. They have, you can do everything from xargs to variables to a number of other things inside of Airflow to actually pass these parameters down. And I'm happy to answer more questions about that. But if you're not using Airflow, there's a couple of others. But the most important thing here is make sure that you're able to actually populate these jobs with the right parameters when they are running on these frameworks. And so finally, I know I said don't rebuild your own SQL processing framework, but you are going to need a little bit of your own scripting, especially if you are going to run backfills, and guess what? You will. Regardless of what data set you have, you will have to backfill it at some point in time. And so typically running backfills, it's easier to do it separately from the day-to-day processing. So your orchestration layer Airflow job is going to take your logic and then run it with all those defaults pushing the data forward every day. But having a script that takes the same logic and the same job and just passes in different backfill parameters is really important, because then you can run that separately from the day-to-day processing without having to pause the day-to-day processing if it's not necessary, and simply patching things historically. Also, by having a separate script, you can run these backfill jobs simultaneously, and multiple partitions you can process within at the same time. Whereas typically with orchestration frameworks, they want to run one version of a job at a time, and you would have to create multiple jobs, which is a lot of overhead that probably don't need. And in this case, just make sure that your unit of parallelism, that partition, is completely disjoint from one another. So if I am updating data for July 1st, I should not be touching July 2nd at all, neither reading nor writing from it. Otherwise, I'm going to run into a problem backfilling multiple partitions at the same time. And I know I sort of jumped the gun on this one a little bit, but having scripting around writing the transformations, usually really important for SQL-based processing. A lot of teams do roll their own SQL templating framework. Just be careful of having to really upkeep this. And this is the hard part here, is the requirements for a framework like this are going to expand. You're going to want to generate more and more complex logic and have more complex expressions. And so at some point, it actually makes more sense to look into something like dbt if you are going to pick a SQL templating framework. And finally, with SQL, you can't really test the logic itself. It's hard to isolate the logic for each individual column that you're outputting. So you're going to have to test the outputs and monitor the outputs. And this is really where a tool like Bigeye comes in to help you monitor the outputs itself rather than monitoring the logic. So with all of that said, with all those concepts in mind, let's talk a little bit about the real world example. So we're going to talk about Uber's experimentation platform use case. So this is something that I worked on for 2.5 years at Uber. We built a system to take records about which experiment each user is in and process those, aggregate them, and then build an analytics tool around it so that our data science teams and our product teams could perform their own analytics around which experiments are driving the most value for the business and affecting which metrics. So to start all of this, we had a lot of raw exposure logs. And when we're talking about exposure logs, we mean logs that are sent anytime an experiment is evaluated for a given user. You can see this diagram on the right there. There was an SDK. You pretty much, that SDK would call our experimentation service and say, what a treatment should I show for this experiment for this user ID? We would return back a specific group, and then we would log an event into Kafka saying this user was just entered into this experiment with this group. Now, that ended up generating, because we had thousands of experiments by millions of users every day, that generated 1.5 here on the slide. By the time that I left, Uber was well over 2 terabytes a day of data and billions, tens of billions of records daily for just these raw logs. And logs were pretty straightforward. They were simply at this time, this experiment, this user entered this group. Now, the problem we had with these is sometimes there was late arriving data because some of this logging was queued, and then sometimes that would arrive late. Kafka, we had cross-region Kafka. Sometimes the replication took longer time. And then other times we just had mistakes in experiment configuration where there was typos and we needed to correct them and clean them up after the fact. And so we needed to not only do that, but also we needed to reduce the volume of data that we were dealing with. And so we would process all of these raw logs into something that was cleaned up. We'd remove a lot of duplicates. We'd clean up a lot of the individual record level things, remap experiment configurations into human readable strings away from integer IDs or UUIDs. And then we'd enrich the data with some experiment metadata. And this processing was obviously difficult. We're dealing with terabytes of data a day that we have to remove duplicates and clean it up and enrich it and spit that out. And then sometimes if we knew that data was became late or somebody made a mistake, in an experiment that started a week ago, we have to reprocess a week's worth of data. And so with that, we needed to design something that would withstand the test of time, both for scaling the incremental processing going forward, as well as allowing us to reprocess the data historically. And so what we did is we picked for that normalized log table, what we did is we picked a partition that's on the date of the log event. Once the log is published, it's not affected by any data before it or afterwards. And so we built a processing framework that just wrote a single day's worth of logs every single time. We could get more granular than that, but we didn't need to. We simply said each run will process a day's worth of data, and that run usually would take about an hour to run. The transformations themselves, we wanted to make sure that we could test them because they are fairly straightforward row level enrichment and processing transformations. We wrote all this in Spark running Java methods over each record, and then we were able to test each individual method. The reason we avoided SQL for this is because there was some fairly complex logic, not the joining, but more around the filtering of what do we consider a duplicate, what is considered not a valuable record or an event that we don't want to store in our process logs. And the most important thing here is we parameterized the date of the raw logs that we wanted to read. Going back to that first data structure, because we were outputting 1 day's worth of log every single time, we would also want to only read 1 day's worth, and parameterizing that allowed us to actually process any day as we see fit. And so finally, when we got to the orchestration level, running the job meant that we would normally run the job for today's date and always just process today's data, and after midnight, we'd process yesterday's data and then today's, but that we would just pass that default parameter through the orchestration framework every single time. And then we wrote a small backfill script that took the same transformation, the same job that we were using to do the processing incrementally going forward. And then that would pass in a user-defined date to read for backfilling. So if I had to reprocess 7 days worth of data because we had late arriving data, for example, then I could parallelize that and run 1 job for each backfill date that I wanted to. All 7 of those would run simultaneously, and I could backfill all 7 partitions in 7 commands that were all pretty much the same thing, or 1 command with a for loop if I really felt like it. So that made it very easy for us to run these backfills. We knew that the logic was exactly the same, so we didn't have to worry about having separate logic for a backfill or for the data-to-data transformations. And so that removed a lot of headache from our backfilling process because we did that work up front to design the data and the transformations in a way that made it easy for us to run the backfills in the future. So that hopefully that put it all together and showed how we on Uber's experimentation platform team applied the lessons that I gave a little bit earlier. My name is Egor Gryaznov. Thank you for participating today. I'm happy to take questions in Q&A. I'll give it a couple of minutes. Otherwise, thank you for joining. All right, I'm just going to check Q&A and chat. All right, nothing in Q&A in chat, so I'm gonna end the webinar. Thanks a lot for attending. We're going to be sending around the link later this week, and the replay is going to be available on our YouTube channel. Thanks again for joining, and have a good rest of your week.